everybody. Super excited to talk about some of the memory things in JavaScript. We know that on a fundamental level, everything we do on the computer eventually becomes binary code, essentially just a bunch of zeros and ones, including everything that we write in JavaScript, such as objects that we create and functions that we declare. But how exactly does that happen? My talk is the result of my own journey down the rabbit hole, trying to understand all of the steps that our code goes through in between to become binary code. And I'll cover the whole journey, starting from the binary code itself and memory architecture in the computer to inner workings of a JavaScript engine like V8 with memory allocation and garbage collection. So there's a lot to cover. It's going to be a fun journey down the rabbit hole with me, and I will show you around. But first, let me introduce myself real quick. My name is Kateryna. I am Ukrainian, but I live in Estonia. I work remotely as an engineering manager at Buffer, leading the front-end direction, and I'm also organizer of Tallinn.js meetup in Estonia. So if you're ever in Estonia, come to one of our events, and you can hit me up if you want to speak there as well. But as I said, we've got quite a lot of ground to cover, so let's start, and let's start at the beginning with those zeros and ones and understand how computers store and represent information. So 0 or 1 is the smallest fraction of information there is. It's like on and off switch, or true or false. In early days, computers used literal light bulbs that glowed for 1 and were dark for 0. And it is called 1 bit of information. And with this binary, we can represent all sorts of data. Small numbers, big numbers, characters, and therefore words and the whole strings and text, emoji, and even the answer to the ultimate question of life, universe, and everything. Okay, you didn't laugh, okay. And there are different types of memory and storage computers use to store these zeros and ones in unique ways. For example, DVD disks use little indentations on the surface that reflect light differently when being shined on with a laser. Or floppy disks use magnetic encoding that can be read by the special head that passes through. But when it comes to the memory our JavaScript applications use, we are primarily dealing with RAM, or random access memory. It is a working memory that CPU uses when running applications on the computer. And let's see a little bit more in detail how that works. RAM consists of these memory cells, and they're essentially kind of tiny storage boxes that can hold charge for some time, with the main idea that we can write to them and read from them. On the hardware level, they are implemented as an electric circuit with a combination of transistors or a combination of transistor and capacitor. And they basically can just hold charge for some time and allow the system to write to them and read from them. But of course, the single cell that can hold 0 or 1 isn't much use on its own. So we can arrange the cells in a grid. And then, to specify which cell exactly we need, we can use the address system. And this is very similar to like street and house address in real life. We can take the first part, it will specify the column that we are looking for, and then the second part can specify the row. And then we can read the contents of the cell at the intersection. So, yay, we just read 1 bit of data. However, of course, 1 bit of information isn't enough for the needs of modern computing. And we need a way to manipulate more bits at once. To do that, we can arrange these grids in an array, and then using the same address, we can access multiple cells at once. So right now, using this 8-bit address, we write 8 bits or 1 byte of data at a time. It's helpful to think of it as a match between the address and the data it holds. And to simplify, we can convert the addresses to the decimal format and represent all available memory as this kind of array of available addresses and their corresponding values. Currently, the RAM that we are using uses 8-bit addresses, which means that in total we can store 256 bytes of data, which is very little in modern computing. This is the example of memory older computers used, often referred to as 8-bit architecture. The modern computers operate on 32 or 64-bit architecture instead, which means that addresses got a lot longer, and therefore they're usually represented in hexadecimal format, like you see right now on the screen. But all the core principles that we just discussed still apply. Important thing to note here is that when applications run on the computer, they don't interface with the physical RAM directly. Instead, the operating system maintains this additional level of abstraction called virtual RAM that maps to the physical RAM under the hood, but gives operating system the flexibility to, for example, reroute some of the data to the hard drive to optimize memory consumption and also provide applications with this illusion of large, continuous chunk of memory available to them. This virtual RAM is dedicated per process running on the computer. And then also the amount can be changed depending on the needs of the application. So now we understand a little bit more how memory works, but more often than not, when we actually need to store something, it wouldn't fit into 1 byte. So then it will occupy a continuous segment of cells in the address space, and is often identified by the first address in that sequence, and is called a pointer, meaning that foo, let's say it's some kind of variable in our code, points to the location in memory where our data begins. And from there on out, we can just follow along until we covered the size of our data. In languages like C and C++, US developers need to manage memory allocation manually. For example, this piece of code allocates memory for an array of 10 integers. What we are doing here is we're multiplying 10 by the size of type integer to allocate the needed memory. And after it has been used, and we don't need this memory anymore, it needs to be explicitly freed. And this is quite a lot of work for you as developer to keep in mind when writing code. But at the same time, it gives a lot of flexibility and power to optimize memory consumption. Now, we talk about C and memory architecture, but if we talk about JavaScript, we don't need to do any of that, right? We can just go around defining arrays left and right, fill them with whatever we want without giving a second thought about memory consumption. And it's actually a good thing. JavaScript is a high-level language, which means that it does a lot of things for us, so that we as developers can focus on building features and delivering value to the users instead of dealing with the memory allocation. And all of the memory allocation and freeing is done automatically for us by a JavaScript engine. And JavaScript engine is just a program that runs within the runtime environment, such as a browser or Node.js, that takes the JavaScript code that you wrote, which is essentially just a long piece of text, and transforms it into machine code that can be executed by CPU. And there are different engines out there. For example, there's V8, developed by Google. There's SpiderMonkey, that is used in Firefox and developed by Mozilla. And there's JavaScript Core, which is part of WebKit and is used in Safari, developed by Apple. In this talk, I will focus mainly on V8, which is arguably the most popular JavaScript engine out there. It is used in Chrome and other Chromium-based browsers like Edge, Opera, and Arc, Node.js and Deno, Electron, and more. V8 itself is written in C++ and is open source. So if you want, you can go and check out the code for yourself. Now we can take this piece of code that declares an object and follow it down the rabbit hole to understand how V8 will allocate memory for it. But first, let's talk about the types of memory that V8 uses. It uses a stack, which is a region of memory that allocates local context when the code is getting executed. And there's also heap memory, which is a much larger segment of memory storing everything that is allocated dynamically, say your objects, functions, arrays, etc. Stack and heap is not something that is unique to V8. These are very common data structures, each with their own ways of adding and accessing the data in the structure. Now getting back to our example, when the interpreter reaches the line with our variable declaration for the rabbit object, it will be already present on the stack and it would need to allocate memory on the heap. And since JavaScript is a dynamically typed language, V8 doesn't know in advance how much space something will occupy in the future. So it will calculate the size based on your declaration plus some internal heuristic to predict how much space this object will occupy. And then the string itself that is present within the object will be stored in a different place, and the object itself will contain a reference or a pointer to that location. And then we can update the pointer in the stack, and our code can continue being executed. You can actually see all of this in the memory tab if you make a heap snapshot in Chrome DevTools. Under the hood, V8, here's our object in the screenshot in here. Under V8, under the hood, V8 uses the superclass called heap object for everything that is allocated on the heap, and contains pointers to all of the values and metadata that V8 uses for optimizing memory consumption. To connect back to what we discussed before, both of these will actually take actual space in the virtual memory dedicated to our process, and by extension in the physical RAM. Of course, as our program runs, more and more things get allocated on the heap. And if we zoom out, stack and heap are located on different sides of this virtual memory segment dedicated to our process. And as our program runs, they grow towards each other into the free space. But also, it's not like our application is the only thing running on the computer. So the memory needs to be shared with other applications. And in the case of the browser, even other tabs or browser plugins that you might have open. It might give a little bit more insight of why Chrome can be so memory hungry sometimes. We can watch that again, yeah. But yeah, now as we kind of had this simple example and we understood a little bit more how the memory is structured, let's go into some more complicated examples and explore more. We are going to stick only with heap from here on out, but under the hood, the stack memory is still there, maintaining all of the local context as the code is getting executed. So we already have our object in here, and let's say we declare another variable with the same string, white. This presents an interesting situation for V8. If we are to allocate a new memory space for it, it won't be very efficient, because essentially we'll be storing the same value twice. So instead of doing that, V8 uses this technique called string interlining. So it detects that both of these are the same string, and instead of allocating new memory, both of them will be pointing to the same location. And this is what most of the variables in JavaScript are. They're essentially pointers to the values that are being stored elsewhere. Now, if we change foo's value to something different, we would need to allocate the space in the heap again, and then foo's pointer will update to the new location. I really liked the analogy from Dan Abramov's Just JavaScript course, where he proposed to think about all the variables in JavaScript as wires that connect variable declarations to locations where those values are stored. So in our case, when foo's value change, its wire gets rerouted to a different place. Now let's explore an example that is a little bit more complicated. Let's say we declare another variable and assign it to the previous object, rabbit, and then we change its name property. If we are to access the original object's name property, we would see that it got changed as well. So when we made an update here, it got updated here too. This is something that is called modification by reference. And sometimes if you are not careful, it can be tricky. To understand why that happens, let's look at the heap. So we have object with two properties already, and this is something that is very familiar to us. We have been kind of declaring similar objects before. But when we declare another variable and assign it to the same object, both of them will be pointers to the same location. So when we update the name property, because it will be updated in the original location, and both of them point to it, it will get updated in both. If we zoom out and look back into our mental model from before, this is what happens. So, and this is a really simple example of modification by reference. To avoid this behavior, we could use a spread operator like this. In this case, when the name property is updated, the original object will keep its original value. The spread operator copies all of the top-level properties, and therefore, when the name gets updated, they both will maintain their original name property. But interesting thing is that it wouldn't work for all of the nested objects out there. So if we have a nested code property within our rabbit object, and then we update a deeply nested property in here, we would see that original object will still get affected. And it happens because something like a spread operator copies only top-level property, often referred to as shallow copying. So when we update the color property, because we used only only top-level properties were copied, and both objects point code or internal object points to the same location, both of them will get updated at the same time. And sometimes it can result in some bugs that are really hard to find. For example, if you're using React and your component accepts an object as a property and you're modifying it by reference, it can backfire in the parent component or even in your Redux store and create some bugs that are really hard to find. And this is exactly why the concept of immutability and some libraries like Immutable.js got popular some time ago, because they make sure that all of the references got recreated and not copied. So we have been speaking a lot about allocating memory. We've been putting a lot of stuff into the memory, but what about freeing the memory that we don't need anymore? For example, in this case, we have this white string that is not used anywhere anymore. And in the languages like C and C++, as we covered before, you would need to do that manually. But JavaScript and V8 runs the automatic garbage collector, which is called Orinoco. And let's dive a little bit more into how that works. But first, we need to understand how V8 can understand whether something is used or it is not used. We can represent all objects we have as this kind of chain of references that goes from the root. And as our program runs, just as an example before, some of those references stop existing. And therefore, some of those parts become not reachable anymore, which means that memory associated with them can be cleared and used for some new allocations. If we look at the memory array and just free the memory that was allocated to this object, it leaves our memory fragmented, meaning there is a lot of little gaps and becomes harder to put anything new into the memory. So to alleviate that, the memory space needs to be compacted so that we have this bigger continuous chunk of memory available for all of the new allocations. If you remember old Windows operating system, there was this disk defragmentary utility that was giving me chills when I was a teenager. Current operating system usually do it automatically, but the process of defragmenting the memory is very similar. Now, as we talked about that, let's talk about how exactly V8 does garbage collection. And all heap is where most of the data is actually stored, is split between two main generations: young generation and old generation. And we'll talk a little bit more why they're called like that and how that all works, but let's focus on the young generation first. It's called young because this is where all of the new objects get allocated. It's fairly small, usually between the size of 1 to 8 megabytes. And inside itself, it is split into two equal parts called from space and to space. And we'll see why they're called like that in a minute. As our program runs, new objects get allocated into the memory. But then at some point, the time comes when we are trying to allocate something, but there's just not enough space for it. And this is what triggers the garbage collector. So V8 stops the execution cycle and starts the garbage collection. First, we need to identify which objects are alive and which are not. So it can go through that chain of references that we talked before and find the objects that are still used. Then we can copy those objects from space to space. And now everything that we had before could be cleared, but before doing that, we need to not to forget to update the references. Then everything in the from space can be safely removed, and we can swap these two spaces in place. Garbage collection cycle can be finished, and we can continue the execution and allocate memory for the object that has been waiting. Important thing to note, because we just talked about compaction, because we copy objects all the time, compaction happens simultaneously, so we don't need to do that separately. As I said before, it stops the execution cycle and often referred to as a stop the world garbage collection. And in the earlier versions of V8, you could actually see a visible lag when, for example, clicking on the button because something triggered the garbage collection cycle. But right now, V8 does a lot of work in parallel and parallelizes it in up to 7 threads at once, and therefore it is a lot shorter and halts the main thread usually for only a few milliseconds. This algorithm is called the scavenger, or is often referred to as a minor garbage collector. It is very fast, but at the same time it's very memory hungry, because we always need twice as much memory to facilitate the work of the algorithm with that from space and to space. which is okay for small amounts of space, but is not sustainable for everything. And this is where the old generation comes in. V8 follows what is called a generational hypothesis, which sounds depressing, but it means that most objects die young. What it means is that objects become allocated and almost immediately become unreachable. And if you look at the way you write your code, you can see those patterns in real life. You have a function, you declare an object that is used one time temporarily, then you return something, and this object is not needed anymore. So we need a way to identify which objects are more likely to stay. And V8 does it in a way that when the young generation fills up and the garbage collection cycle is run, the objects that survive the cycle are marked as intermediate. Then, as the young generation fills up again, and we run the second garbage collection cycle, the intermediate objects that, if they are still alive, instead of staying in the young generation, will get promoted into the old generation instead. Statistically, I found some data that around 20% of the objects survive into the old generation. But now let's talk about the old generation itself. It's a lot bigger, and it actually takes most of the heap. And for the garbage collection algorithm, it uses mark, sweep, and compact algorithm. And the garbage collector here is often referred to as major garbage collector. Let's talk about marking first. What V8 does, it traverses through all of the chain of references from the root and marks the ones that are still accessible. Then everything that is not marked, the memory associated with it can be used for the new allocations. So it can be swept, hence the sweeping part. But the way free memory is managed is actually really interesting. So let's look into that. The whole heap is divided into these sections that are called pages. And each one of them is basically a segment of memory available for the allocations. And when the memory is freed, or basically something that was stored there is not needed anymore, there are these gaps that can be used for something new. And instead of going through the old memory and finding those gaps, V8 maintains this structure called the free list, which is like Airbnb for memory locations. It basically maintains a dictionary with all of the free locations available categorized by size. For example, here we have 3 locations of size 1 available, and then 3 locations of size 2 available. And of course, there's a lot more sizes than that. So when the new object comes and it needs to get allocated, we detect its size and find the first suitable location of the appropriate size, and then we can allocate the object in that place. Then, of course, this location needs to be removed from the free list because it's not available anymore. And we can continue our execution, because the object has been allocated. But also the compaction bit is also really interesting because we haven't kind of here compared to the minor garbage collector where the memory was compacted together with cleaning, it doesn't happen anymore. So as our program runs and we free more and more memory, some of the pages can become too fragmented. And V8 runs this internal heuristic that detects the pages that are at the risk of becoming too fragmented. And then it runs compaction on them as needed. So let's say this is the page that was detected by V8. It will allocate the new page and then copy all of the filled values from this page to the new page. Now everything in the old page can be deleted, but before that we can of course need to update all of the references that were referencing data stored in the old page. Now we have this bigger continuous chunk of memory that is available for the new allocations. It gets added to the free list and it can be used. And as we talked a little bit about how that all happens, let's see how it is executed by V8. So as the heap limit is approaching, V8 splits the marking work and does it concurrently. Then there's, of course, this little bit that still needs to be done in the main thread. But once marking is done, sweeping can be done completely concurrently because it does not affect the execution. Everything that we are doing is we are just adding locations to the free list. But compaction is actually really tricky because it involves updating all of those references. So it is done in parallel over multiple threads at once. And then once everything is done, execution can continue. In terms of performance, as a lot of work is done out of the main thread, it's usually fairly fast, but of course really depends on the size of your heap. Now we've covered both minor garbage collector and major garbage collector, and this is where I would like to wrap up my story, but before we finish up, and you can go to lunch, let's do a little bit of recap. So the code we write in JavaScript is essentially just a long piece of text. By itself, it doesn't do anything. It needs to be executed inside a runtime environment, such as a browser or Node.js. And within that environment, there is this little program called JavaScript engine, like V8, that takes that code and processes it to transform it into machine code that can be executed by CPU. Within itself, it stores values in stack memory and heap memory. Stack is used for all of the local execution context, and heap is a much larger segment of memory allocating everything else. Then we are not only allocating things, we also need to clean up stuff that we don't need. So V8 runs automatic garbage collector, and there's two garbage collectors out there. Minor for the young generation, for all the new objects, it is very, very fast but memory hungry. But then there's also a major garbage collector that uses mark, sweep, and compact algorithm for the rest of the heap. Then that is actually transformed into the virtual memory array that is dedicated by operating system to our process. And then that memory actually maps to the actual cells in the actual RAM memory card stored in your computer that stores those zeros and ones. So I aim to cover quite a lot of ground and give you the overview of the whole journey of how the variables that we create go through to get turned into zeros and ones. But there's so many opportunities to dig deeper and to learn more. And if you're interested, I really encourage you to do so. And I will share materials with the additional resources and links and articles in the chat in this Vito application that we have. But I hope you enjoyed this overview, and it gave you a little bit more insight of all of the things that happen behind the scenes and appreciation for the amazing tools that we have at our disposal as developers. You can find me on this social media, and all the questions, ideas, and feedback is very welcome. So thank you for the attention, and have a good lunch.